Hello. This video will be essential viewing for anyone completing a practical investigation at school. I have another video which describes the differences between accuracy and precision in more detail, but briefly, accuracy is how close a measured reading is to the true value, and precision is the smallest unit that can be measured with the instrument, or the spread of results if you've taken and found that they vary. An absolute uncertainty is measured in the same units as the thing you're measuring. For example, if I was measuring the length of something and I documented these readings, then you can see they vary. It would be sensible to quote the value as the mean of those readings, and I've also determined the absolute uncertainty as half of the spread of the range of readings. Note that absolute uncertainty is always quoted in the same unit as the measurement, here centimetres. You may make mistakes from time to time, and a mistake is not the same as an error of measurement. If I took a result here and it was clearly a long way out from the others, I would discount it before taking the average. I would go back and check and see what had caused this error or mistake. Now, sometimes the readings may be exactly the same. If I'd measured the length of something with this ruler and found they were always 90.2 centimetres, does that mean there's no absolute uncertainty? No, of course it doesn't, because I cannot measure accurately with a ruler. I can't measure more than to the nearest millimetre with this ruler. So, for convenience, we would often say the absolute uncertainty can be taken as the smallest unit that the instrument can measure. You can argue that half of the smallest unit is also suitable. For example, these measurements 90.2 centimetres, I might quote as 90.2 plus or minus 0.1 centimetres. That's a millimetre, but I will always quote in the same units. So I have estimated the absolute uncertainty of this ruler. Now, if I'm measuring something that's very still and isn't likely to move and it's square onto the ruler, then I could measure it to the nearest half millimetre perhaps. But you might argue plus or minus a millimetre is suitable. So with different instruments you can argue that the estimated absolute uncertainty is the resolution of those instruments. These digital vernier calipers have a resolution of 1/100th of a millimetre. So even if they all measure the same thing and I repeat measurements 3 times, I would quote the absolute uncertainty as the smallest increment they measure. Measuring time with a stopwatch, you do not really quote the uncertainty as the resolution or 100th of a second with this sort of stopwatch, because you've got reaction times. And so the minimum absolute uncertainty would probably be quoted as 0.01 seconds. You might take 5 repeats and find that the actual spread is more than that. Now we can calculate a percentage uncertainty as a percentage of the average value. So that's fairly easy to work out. You take the uncertainty and divide by the average and multiply by 100. So this example I'd express as 0.22% uncertain. Now, percentage uncertainties are useful for combining in certain situations. I'll give you some examples where you combine absolute uncertainties first. I measure the length of this book as 10 centimetres to the nearest centimetre, and say I had a rough ruler that didn't have millimetres on it. If I took 3 books in a row and I wanted to know what the total length was, you can see I have measurement uncertainty of each of these books if I measured them one by one. Therefore, the total length would be 30 centimetres plus 3 centimetres of uncertainty, plus or minus 3 centimetres. So when adding data, you would obviously add the absolute uncertainty, because in reality, this book could be 9 centimetres, 9 and 9, and I get 27, or they could be 11 centimetres each. What about when you subtract? Now, if I'd measured all 3 books with one longer ruler and found it was 30 centimetres plus or minus 1, and I measured another book on its own as 10 plus or minus 1, what certainty have I of the length of 2? 30 take away 10 is 20 centimetres, but how uncertain am I? you would add the two uncertainties when subtracting, because this value could be 29 to 31, this value could be 9 to 11, and so this value could be as small as 18 or as big as 22. So again, when subtracting data, you add the absolute uncertainties, noting that absolute is in the same unit of measurement as the value. What about when multiplying to give the area? So 10 by 10 centimetres, I would clearly have 100 centimetres squared, but how uncertain? Well, this value could be as small as 9 and as big as 11. So the area could be 9 by 9, or 81, or 11 by 11, which is 121. And you see the average, the mean, is 101. It's almost 100 centimetres squared. In fact, it is 100 to two significant figures. And the uncertainty is 20 centimetres squared. So you can see I've got 10% uncertainty in the length and 10% uncertainty in the height, and I'm 20% uncertain in the area. So I can quote the result as 100 plus or minus 20 centimetres squared. So when multiplying or dividing data, you would add the percentage uncertainties. And you can see how that gives you a much simpler way of doing things, particularly with more complicated data. If you were raising data to the power, you would multiply the percentage uncertainty by that power. For example, 10% uncertain in the length, 10 squared, I'm now 20% uncertain in the area. Now that means if I am raising to the power of a half, for example, the uncertainty would decrease. And that is true. It's the only situation where uncertainty in a measurement can reduce. Hope that helps.